in fact, if we compare the production efficiency of a warm-blooded animal to a cold-blooded animal, so here is a caterpillar and a squirrel, we're just putting cold-blooded animals as invertebrates in this case. We look at the use of 1,000 joules of energy, so we can think about it as 1,000 calories as well. The caterpillar is going to use 180 calories to grow. It's going to dispose of about half of those calories. It's not going to be able to digest them or use them for energy. And it's going to use 320 calories for its life processes, moving around, other biological processes that it is undergoing internally. Now let's look at the squirrel. The squirrel is going to consume the same amount of, so we're comparing directly 1,000 calories. So from the consumption of 1,000 calories of food that the squirrel has, it will excrete 177 of those. It's going to use 784 calories for cellular respiration, so a great deal more for the biological processes that are going on inside its little squirrel body. And it's only going to have 16 calories left available to grow. So that's a pretty significant difference when we look at the 180 versus the 16. And again, to calculate the production efficiency, we're going to divide 180 over the initial 1,000 that we started off as. So from 1,000 calories of food, 180 in the invertebrate can be used for growth, right, for actual matter. And for the squirrel, for the vertebrate, only about 16 out of 1,000. So that should give you an idea of how different production efficiencies can be. So what is the implication of that on our lifestyles? If we are interested in conserving the amount of energy that we put into culturing and cultivating our food, we, just from these numbers in this nice diagram here, we can already see that consuming food farther down in the food chain is going to have a much more efficient transformation of energy from the energy that we started off as to the amount of matter that we are actually able to consume. And that can be seen in many different ways when we look at the values of the food that we consume and how many resources go into them. So, for example, one resource is land use, so just the amount of land that we use for agriculture. And we can see that per meter squared, beef takes up by far the most amount of space. So conversely, if we look down here, pulses are beans, lentils, and peas. They take up the least amount of space, and we're comparing directly the amount of protein that can be harvested from that unit of space. So for 1 gram of protein, from a steak, we need about a meter squared. From 1 gram of beans, of protein from beans, we need about 1/100th of that. And again, that's because of that inefficient transfer of energy that we have in our trophic pyramid. So in a biomass pyramid, each tier will represent the actual mass of the total number of organisms at that level. And most biomass pyramids, as you would, I'm sure, very astutely predict, decrease very sharply as you move from one stage to the next. And that explains why, usually when we have tertiary consumers, their numbers are very few, so the amount of energy available to them is quite low. So primary consumers, the number of organisms, or the total biomass of organisms of primary consumers, such as grasshoppers or locusts, is going to be much, much higher than the total biomass of birds of prey, for example. So only 1% of the chemical energy fixed by photosynthesis. And what is photosynthesis? I'm sure you remember. It's the conversion of sunlight that plants do to convert sunlight into matter. And only 0.1% reaches those tertiary consumers. So which law of thermodynamics explains that phenomenon? Do you remember? A pyramid of net production represents the loss of energy with each transfer in a food chain. So again, let's think about what this means for how we obtain protein, what this means about our food consumption. So like we saw before, this is just a different way of seeing the same data that I showed you previously. The amount of protein, well, it's reversed. So here we're looking at protein per acre. Before we saw amount of land per gram protein. The numbers don't exactly add up. I think a lot of these quantifications, I try to find reliable sources, but there's a lot of variability in how people measure or the type of quantifications that they choose to have. So it's good to see the data from different sources. Okay, so usable protein per acre land. So soybeans by far are the most efficient harvest of protein that we can get per unit of land, per unit of agricultural space. Down here in the lowest bar is beef. Yep, it's beef. Okay, so eggs, milk, right? Any animal products take up a little bit more space. Any plant products take up less space, and we're also looking at some sources of complete protein. And how is our land used? So we're going to have a whole unit on land use, but this is a nice little introduction. So let's look at the global surface area allocation for food production. And what's kind of interesting is that here's the Earth's surface, here's all the land that's available to us. 71% of that is actually usable. Some of it is glaciers and areas that people would have a very hard time surviving without a lot of technology. Plants certainly probably have a very hard time surviving there. Of this habitable land, according to these numbers, we use about 50% of that for agriculture. I've seen other numbers that are as high as 70%, so we use a lot of our land for agriculture, and we are having more and more people on Earth, so our demand for food is going to get higher and higher. So think about that and what that means about how we want to allocate our space to agriculture versus just habitats for human beings. So of this land that's designated for agriculture or dedicated to agriculture, about 3/4 is used for livestock and 1/4 used for plant crops. And if we look at the distribution of how people gain their food and how people are gaining their caloric supply, most of it is from the plant-based food and a little less of it is for the livestock. So even though we've allocated all of this space for livestock, not a huge source of food because it is a very inefficient way of growing our food. Okay. Another resource that livestock uses a lot of is water. So if we look at the gallons of water consumed per pound of food, hamburger beef is a lot higher than rice, for example. So 1 pound of hamburger beef takes about 2,500 gallons of water. And if you look at your average household consumption per person, so what probably you as an average American use per day, just flushing your toilet and washing your dishes, you probably use about 100 gallons a day. So 1 pound of beef uses 2,500. And so you can think about what the implications are for us as a society, how that's going to affect us and affect our future. In the last part of the ecology module, there's a page of additional resources, and you can read a bit about how people are proposing to help mankind, help the entire ecosystem by coming up with different sources of protein that people would be willing to eat. And I think some of the solutions are quite inventive, so I hope you enjoy reading it.